Okay, these are notes on the paired T distribution. We're on page 135, and this will be the introduction to the paired T distribution. So first off, paired data, what is it? Data, and basically data is paired when the observations are collected in pairs, two samples uh, or observations in one group that are naturally related to observations in another group. Now, I don't know about you, that's a mouthful of words that doesn't make a whole lot of sense. So how do I recognize when paired data arise? Well, basically, usually what's happening is there's a subject is measured twice. So typically there's a before and after, and then the treatments and the difference are computed for each. So it's like how, with the old medicine, how long did it take until the pain go away? And then I took the new medicine, how long did it take the pain to go away? And they subtract the difference for me individually, and that would be a paired difference. Um, and so that would be a subject tested twice. There's the before after situation. Pairing sometimes also occurs with naturally occurring couples or pairs, but it's really important they are paired together. It's not one group compared to another group. It would be me compared to my brother or me compared to my spouse. We really like twins in studying. Why? Because they're biologically similar. So we tend to give one treatment to one twin and one treatment to the other twin. And then we measure the difference in outcome between the two. We sometimes, like I said, will do it for spouses or siblings. Um, One thing to notice is when you're running a match pair, the data list, there will be two data lists that they give you, and the data lists have to be the same. There'll be the data list before you got the data treatment, before you got the treatment, and the data list after you got the treatment. So those two lists may be the same, must be the same length. Now, just because they're the equal length does not mean you're running a paired test. But to run a paired test, the data links have to be the same. So that's kind of the first check: is are they the same length? Because if they're not the same length, it's not a paired test. Um, when they give you the two lists of data, you're actually going to take your before for one minus before for the after, and take that difference and continue to do that over and over again for each paired. From there, you'll compute an average. We've actually worked with paired data before. We talked about the match pair design, and we did it for waterproof boots and for mosquitoes. And the question is, why did we do that? Well, we did that to control for differences for the individual. Consider the mosquito person. We know that some individuals are very susceptible to mosquito bites and some are not as susceptible. So I sprayed one spray on one arm and another spray on the other arm, and that individual got tested twice and it counted the difference in mosquito bites from left arm to right arm, and that was a match pair. With the match paired boots, we're controlling for differences in the way people, where they worked, where they lived. And so basically match pair design is extremely powerful. It controls for much more than any other design. And we should use it all the time, but it's not always available to us. But when possible, we should be definitely doing a match pair design. And that's what it says here. Lastly, the very end, if the data is paired, we do not take the mean of each sample and then compare the mean. So we're not going to take the mean of sample one minus the mean of sample two. No, that's incorrect. We will not be doing that. That is a different type of test. That's a two sample test for means, which will be in about 2 weeks. Right now, we're just taking each sample value and subtracting its pair from it. I'd like to look at the recipe sheet very quickly before we actually get going. And mainly to point out that it's very, very similar to running a regular t-test. So first off, here instead of a mu equals, we have a mu d equals, so it's the mean of the difference equals. And by the way, except for very, very rare circumstances, when we're talking about a match pair, but for match paired, we are almost assured that this is going to be equal to be 0. And so our alternative is going to be less than, greater than, or not equal to. And the reason it's 0 is because the assumption is that there's no difference. So because the assumption is there is no difference, we say that it's 0. Random sample, that didn't change. Ends less than 10%, that didn't change. But we added a new one, and it is the differences are independent. And basically they're saying when you find one difference, it should not impact the next. Pretty straightforward there. And then we have our normality. So this is our typical normality that we finished up. Originally, we were working with a formula that looked like T equals X bar minus mu S divided by the square root of N. All we did here was drop some D's on it, and basically the mean of the sample difference is the mean of the population difference. The standard deviation of the differences of the sample differences divided by the sample size. And basically the sample size is the number of differences. So if you're given 2 strings of data, it's after you subtract them. All right. We're going to enter the data in the calculator, and basically you're going to have to enter into one in the L1 column and the other in the L2 column. And then you're going to go to the top of L3 and do second L1 minus second L2. This is completely new. I'll show you how to do it. It's not difficult, but you need to make sure you're using it. To get your actual values, StatCap 1 variable statistics, and now we have L3. We were using L1, so this is a change because we're now using L3 because that's where our data is hidden. And then we're going to do the stats test, t-test, and highlight data if data is used, and copy our things down, etc. And we have the p-value is, and everything else follows the same. All right, so that's going to conclude, and basically everything else is exactly the same. We're going to need to restate our definition. We're going to need to restate the alternative hypothesis. So everything is going to be pretty much the same once we enter the data in the calculator. All right, so that'll conclude this, and we will go ahead and start the we'll start a scenario just in the next video.